Hey everyone, welcome to day 2 of virtual learning. Today is your first time though getting an ed puzzle this trimester, so that's pretty awesome. I'm sure all of you are very excited about watching an ed puzzle and spending some time doing that and answering a couple questions. So I will not, I won't take too long to put a question into this ed puzzle. Anyway, in all seriousness, I will try to make this lesson fairly concise, and I will go as quickly as I can. So I probably will talk pretty fast, and yeah, that's kind of how it goes. Last trimester, some students made the joke that that virtual Mr. Lehman talked super fast, and it was like I was on fast forward times 2, and in person Mr. Lehman is on like the speed 1/2. So that's kind of interesting, but I actually will try to make it go pretty quickly so that you guys don't have to sit behind a screen any longer than you have to. Today we're looking at lesson 6.7, which, as you can see, is called Modeling with Exponential and Logarithmic Functions. Today is really application day. I mean, we're not technically learning anything new. If we were in person, we would learn some new things that we can do with a calculator and to help model some of these exponential functions. But since you guys are all at home and not everyone has a TI-84 calculator or a graphing calculator, then we're going to have to skip that calculator version or that calculator part and hopefully come back to that sometime when we are in person. So we're just going to look at a couple things today, and then we'll move forward. Today, the learning targets are to be able to classify sets of data. We will also look to try to write exponential functions. That's something you already know how to do, but we're going to look at it with a little bit of a twist. Students will be able to I can't yawn. It's only 2:20. Okay. Students will be able to use technology to find exponential and logarithmic models. That is unfortunately not something that we're going to be able to get to today, because I didn't find an app that was similar to like a TI-84, and I don't want to spend a bunch of time showing you how to graph these on your iPad when we're going to need to know how to graph them on our calculator. So hopefully we'll get to do that soon. What today is going to look like, and if you look at these slides and everything, today is going to be very similar to, what day was it? Oh, it was a couple lessons ago. It would have been the last lesson, but it was about 5 days ago, where we just looked at examples and where we had like 6 or 7 slides, and it just was an example of different types of problems that you'll see on the homework. So I know that lesson took a while, but again, I'm hoping to make this go a little bit quicker today. So let's look at our first example here. Determine the type of function represented in each table set. So when you guys saw a question like this in algebra, what you look to do was look at the constant, not look at the constant difference, but look at the difference between each of these y values. Now, we just assume that the x is consistently going up by the same thing, because most of the time it is, but still we need to double check to make sure those x's are consistently going up by 1 or 2 or whatever. Then we're allowed to move on and look at the y's. So we don't always just want to completely take that for granted, that the x's are moving how they should. So when we look at the y's, we will see that from 0.5 to 1, that's up by 1/2. From 1 to 2, that's up by 1 full. So we know that it's not a consistent difference where we are adding. If we are looking at multiplication, we're multiplying by 2, multiplying by 2, by 2, and we see that this pattern holds. So if it says determine the type of function represented by the data, if we're consistently multiplying by 2, that means that we would be looking at an exponential function, right? We would have a growth factor of 2 or a common ratio of 2, and that would be exponential. So that one was pretty easy. We know, kind of on a side note, if it was consistently being added by 3 each time, whatever the data was, we would know that that's linear, but that is not our focus for right now. Now if we look at part B, here we are going -2. Oh, whoops, we're not going -2. Yeah, we're going -2, +2, +6, 10. Let's see, 14, 18. So we have quite a bit of change going on. So what we look to do in this situation is look at the second difference, and hopefully that's a familiar term from algebra. But here we are adding 4, adding 4, adding 4, adding 4, and adding 4. So we will see that our second difference is 4. If you remember again back to algebra, we know that a second difference has to do with quadratic function, and that is what we would be dealing with here. If we're not exactly sure, we also could graph this, and if we look at our graph, we're at 0, 0, at -2, 2, +2, 2, and we can see how that quadratic would form with its vertex being right there at 0, 0. So you'll have a couple questions like this on your homework. Determine the type of function represented by the table. Oh, jeez. By the table. So a little bit of review there. Other types of questions you'll see on the homework, and this covers like 6 questions on the homework, so probably majority of your homework deals with this right here. Write an exponential function, y equals ab to the x, whose graph passes through 1, 6 and 3, 54. So we know that this is the form that our equation has to be in. We know these 2 points both have to be on that exponential function. The way that we try to write an equation is, again, we know it has to be in this form. We know we need to find numbers for a and for b. So here's what we would look to do. If we take this first point, we can plug x and y into our equation. And we can also do that with the second point. Now, we have a problem. We can't just plug one into the other yet. We need to find one of these variables. So what we look to do is to try to find a. And we're choosing this top equation to solve for a because b is just to the 1 power, the first power. So really we can rewrite it like this. And if we're trying to get a on its own, it would look like this. Again, we'd like to use our equation that has b just to the first power so that we don't have to have like a b cubed here on the bottom of our fraction. So now that we have a isolated, we can plug it in for a in this equation. So 54 equals 6 over b times b to the third power. 54 equals 6, and if we simplify here, we just have b squared. 54 divided by 6 would give us 9, and b would equal 3. So if we write an equation or a function in this form, we still don't know what a is, but we just found that we'll have 3 to the x. Now to figure out what a is, we can look back to what we solved for here. Right? We know that a has to equal 6 over b. So if we plug our 3 in for b, we'll find that a equals 2. And now we have an equation. Right? We filled numbers in for a and for b. So that process right there is going to be something that we'll use throughout the lesson today and will be mostly what we look at on your homework. Let's look at a third example. A store sells trampolines. The table shows the numbers Y of trampolines sold during a certain year that the store has been open. Write a function that models the data. So in this case, they don't give us two specific points to use. So we need to choose 2 points from this table to write an equation from. So why don't we choose 112 and 436. We could choose any points, but I'm going to go with those. I say we could choose any points, which is true, but we definitely want to choose a point where x is 1 if possible, and that is just because then we have one of our equations has a b value that is to the first power. Just makes it a little easier to simplify. So we know it has to be in this form, our final equation. So let's take our 2 points that we have and plug them in. So we know that 12 equals ab to the 1. Also, we know that 36 equals ab to the 4th power. Well, if we go over here to get a by itself and to solve for b, we can do that, and now we can plug a in. Guess I don't need those parentheses. And this would simplify just to 36 equals 12b to the 3rd power. Now, just for the sake of time, I'm not going to go through everything, but we would find that b equals the cube root of 3, and this is approximately 1.44. Now to find our a value, 12 over the cube root of 3 would be about 8.32. So we can write our equation. Here's our a value. We just found our b value here. So we could write our equation to model this data. Remember, trampolines sold in a year. And we can model that data as y equals 8.32 times 1.44 to the x. Now, one thing, it's an image that I'm missing from the textbook. There we go. Which I've got on my computer screen. Well, can't I just go like this? Perfect. Now it's on our slides. Where's my pen? There we go. Like this image says, a set of more than 2 points fits an exponential pattern if and only if the set of transformed points x ln of y fits a linear pattern. So what we are getting into now is a line of best fit, which I do not think you guys have seen before, but a line of best fit means that we could have a set of points, like an exponential set of data, and we are trying to write a line that averages those points. Okay, and makes a line of best fit, a line in the middle of those points. Now, in this section, they don't use the word line of best fit, so you won't see that come up. But I think down the road, eventually, if you haven't looked at it already, that's what this will lead into. For now, we're going to stick with this. A set of more than 2 points. So like here, we have y equals 2 to the x. Fits an exponential pattern. So this new line fits an exponential pattern if and only if the set of transformed points x, and for every y we take the ln of it, fits a linear pattern or makes a linear pattern. If we take each of these points from our exponential pattern, put them into x and then ln each of the y's, and it gives us a line, then we know that the exponential pattern and linear pattern fit each other, that we have a line of best fit. So this is what, well, let's see, is this our example? Yeah, it is our example. This is the last example, and I'll just wrap up with a few things and I'll get you out of here. Use the data from example 3 from here. Create a scatter plot of the data points x ln of y to show that an exponential model should be a good fit for the original data pairs, x, y. Then write an exponential model for the original data. Now, I didn't go through, or we're not going to go through and make the table, but if we look at, what's the first point? 112. The first point is 112. Now, x stays the same, and then to find our new y value, we take the ln of 12. So that's where this comes from, like you saw. ln of 12 is just 2.48, and they would go to do that with each of those y values, and that's where these points all come from here. All right, they're creating this line right here that is a best fit, or that best models this data in a linear form. So now with this line, what they have us do, it says write an exponential model for this data. And you're probably thinking, well, we have a line here, so how are we going to write an exponential model? Well, you'll see. Let's just start by writing, well, let's start by thinking about it by writing an equation of this line. So we can write an equation for this line, y minus y1 equals m x minus x1. This is our, let's see, this would be slope intercept, nope, point slope form. So if we choose 2 points on our line, let's say we choose this first point, and let's say we choose our last point. We choose 2 points on a line, we can find our slope. In this case, our slope would be 0.35. And then we can plug one of these points into our equation, and we can write an equation for this line. So let's do that. Let's take, which one would be easier? Well, probably if we take 1 and 0.48. So y minus 2.48 equals 0.35 x minus 1 would be our regular equation, right? Now, one thing that we have to pay attention to, like it says right here, is we ln'd each of the y values. So when we are writing our equation, this initial equation, we cannot just leave this as y. Each y value is ln'd. We take the natural log of. So we have to, when writing this equation, put ln around our y. Now, like anytime, we need to try to get y by itself. So if we distribute and bring this to the other side, we would get that the ln of y equals 0.35x plus 2.13. Now to continue to get y by itself goes back to the solving equations that we, well, not necessarily solving equations, but a little bit of the solving equations that we worked on yesterday. But we know that to get rid of this ln, we need to raise both sides to the power of e, so that ln and e can undo each other. So we have y equals e to the 0.35x plus 2.13. Now technically this is correct, right? This would give us, I mean, we got it into y equals, but they would like it in the form y equals a b to the x. They would like it in that exponential form. So to get this in exponential form, we need to use some of our simplifying rules. We can rewrite it as y equals e to the 0.35x times e to the 2.13. Since, I mean, we can split this up, because if they're being multiplied and they have the same base, we add those exponents, right? That is our rule. So that's why we're allowed to split it up. Now if we simplify e to the 0.35 x, we could split that up as well. Whoops, I want to backtrack. I don't want to split those up. My fault. I don't want to split that up one more time. We just want to simplify from here. That's why I stick to my notes. If we simplify here, e to the 0.35, we get 1.42 to the x. E to the 2.13, 8.41. And there we have it with our a value and our b value. Now I know that seemed like a lot. Your homework questions are not going to be, well, your homework questions are not going to be most full of problems like this. Most of the homework questions will look like this. So you'll have, I think it's 2 problems like this, 6 problems like this, either 1 or 2 application problems. And then there's a problem that asks about graphing and things like that, but you will need a calculator for it. So you'll see in the description of the homework that I said to skip the last problem. These last 2 examples that I have are both questions that you need a calculator for. So instead of solving by hand for this line of best fit like what we just did, you actually can plug all of this into your calculator and it'll make the equation for you. So it's cool to know how to do it by hand, but we will not be doing it by hand very often. We will plug the points in the calculator and we'll let it do the work for us. But also you should feel sweet because you can do that by hand. So I know that was a lot. I know I was talking pretty quickly, but hopefully you got the meat of the lesson that you need, that these examples here are really what we need to look at. If you have any questions, make sure you let me know.